So today I'm going to talk about robust classification under dataset shift. This is some work that we do jointly with Tigran from YerevaNN and Greg Verstig and Aram Galestian, our colleagues from University of Southern California. Okay, so I will quickly introduce what is dataset shift and what are some of the types of the dataset shift. Then I will describe one type of dataset shift that we are working on. Then I will quickly show an algorithm that we developed and then show the experiments. And finally, say a couple of words about a new benchmark that was proposed to measure dataset robustness to dataset shift this year. So what is dataset shift? A common assumption in machine learning that we sometimes forget is this IID assumption. The idea is that there exists some distribution P of X and Y, and all our sets that we use in the training and validation, so training set, validation set, test set, all of them consist of samples which are sampled from the same distribution. Okay, so this is a very nice assumption, and under this assumption, it is reasonable to expect that if you have a model which is trained on the training set, it will perform well on the test set also. And most of the machine learning research, both in theory and practice, is based on this IID assumption, even sometimes without explicitly mentioning it. The problem with this is that this assumption rarely holds in real-life scenarios. So what can go wrong here? There are many ways this can go wrong. I tried to classify them into two cases, although this is not exhaustive and these are just examples. So the first thing is that this distribution of P of X and Y might change over time. Okay, so imagine an example from medical field. So suppose you are training a model which tries to predict some disease based on electronic health records or something, and you have like 100 diseases you want to predict. One problem that can go wrong, the prevalence of diseases might change over time. So for example, this year there will be a lot more pneumonias, and especially COVID type of pneumonia, than you could have earlier if you collected your data set like last year. Another example from self-driving cars. So you know that when we're training models for self-driving cars, we want to recognize all objects in the scene. And imagine that we have a classifier which detects bicycles on the street, and we notice, or sometimes we don't even notice, that this classifier of bicycles works well when the bicycles are, for example, white and gray and black, and not very well when the bicycle is green. But then imagine a company like Yerevan Ride appears and half of the bicycles in the city become green. So if we had like 5% error in recognizing green bicycles on the road, suddenly this 5% becomes significant because most of the bicycles are green, and we do not recognize most of the bicycles, which becomes a problem. Okay, so these are the things that change over time, so that whenever you collected your data set, you were not able to predict that this kind of changes might happen next. But there are also issues where you have some bias in your data collection process. Again, from medical example, you can imagine that whenever we collect data from some patients, obviously in the test set or in the real life scenario where we are going to run this model, we will have a different set of patients, right? So if for somehow our model overfits on the patients that were in the training set, it is not going to work on the patients that appear in the test set. So this is very important. I think Arsen's presentation explicitly mentioned this yesterday when they were talking about invoices, so that they they split this dataset of their invoices by companies so that the invoices appearing in the training set and in the validation set come from different companies. This will help to make sure that you do not overfit on invoices from the existing, from some subset of companies, and your performance on the validation set will always show you that you are doing something wrong. Another example from self-driving. So imagine that we have collected a large training set, but all of these images in the training set come from, for example, only 3 types of cameras. But imagine we are a software company and we are creating software to sell it to many different car makers, and other car makers can have other types of cameras on their machines, on their cars. So how do we make sure that our models will work on data that comes from other cameras? This is another type of dataset shift. So these scenarios are called dataset shift, or in other literature, you can find distribution shift. And the goal is to learn robust classifiers that can survive such shifts. A natural question arises, what kind of shifts we can survive? It is obvious that we cannot be robust with respect to all kinds of shifts, right? Like if we try to give an extreme example, it's obvious that, for example, if you have images in your training set and you have text in your test set, you can't generalize, right? And this is also technically a dataset shift because the distribution of your inputs changes from images to texts. This is like a very extreme example, and obviously we do not expect to our machine learning models to work there. But obviously there are other cases which should be manageable. So if we characterize properly the type of the dataset shift, we should be able to work with it somehow. There is a book we found, it's from 2008. It's called Dataset Shift in Machine Learning. It describes many types of dataset shift, but the best thing I like there was the way they suggest to characterize the shift. They say, let's draw the dependency graph of the random variables and let's color the variables that produce this shift. Let me give an example. This is a type of a dataset shift which is called label shift. You see, we have X, which is our data, and we have Y, which is our labels. And you can see that there is an arrow from Y to X, which means that Y causes X. So we have some causal relationship. And Y is colored with a darker color, which means that Y is the variable that is going to shift from training set to test set. Okay, so if we try to describe this formally, let's denote by P and Q the training and test distributions. So P is the training, Q is the test. And we can decompose P, the joint distribution of X and Y, the following way. We have P of Y, and then we have P of X given Y, the conditional, and the same for Q. And label shift assumption says that the distribution of Y is going to change, which means that P of Y does not equal to Q of Y. But then the rest is not black, is not dark, which means that the rest is the same. So the conditional distribution of X given Y is the same in the training and test sets. So this scenario is called label shift. This means that the label distribution can change. A good example of this is the disease prevalence shift. So imagine some disease becomes more common at some point. So if we had like 1% of pneumonia last year, this year we have 10% of pneumonia. It means that the distribution of Y is changed. And this can cause problems, but this setup is relatively well studied. There is a recent paper by Zach Lipton and his team. It's called Detecting and Correcting for Label Shift with Black Box Predictors. So basically they show a way how you could detect that label shift happened in your test set, and allow to correct for that and basically stay more robust. Another type of domain dataset shift is called domain shift. This is probably quite popular. So here, let's look at the image first. We have X, which is our data accessible to the training set, and we have Y, which is the labels. But imagine that X actually depends on some underlying variable x0, which we do not have access to, and X depends not only on x0, but also on some function f, which kind of acts on x0 and produces x. Okay, so imagine here, equation number 5, it says x equals to f applied on x0. Here, f can be interpreted as a measurement of x0. So imagine there is some real-world object x0, and we measure it somehow. For example, we take a photo of it, and this measurement is f, or taking a photo is f, and f is the one that is colored with a darker color, which means that that's what is going to change from training and test environments. So a nice example would be you changed your camera. Okay, there is x0. We don't. Our dataset does not contain the real world x0 information. We only have the pictures of x0, which is taken by camera, and then in the test set we have another camera, which is probably different. It has slightly different colors, or in other cases it's very different. So imagine you have an RGB camera, and then in the test set you have infrared camera. You capture the same object, but you get a quite different image. And that's what is your X. This is called domain shift. And a type of this problem is very well studied. That's the case when we have access to P of X and Y, so we have the full access to the training set, but for the test set we only have basically the images, but do not have the labels. This is called unsupervised domain adaptation. So whenever you have images and corresponding labels in one domain, and for the other domain you only have the images, but you do not have the labels, there are ways that you can somehow transfer your knowledge to this test set. But you need to have access to your distribution of the test set. So not a single image, but the whole test set, but only the images. This is called unsupervised domain adaptation because it is unsupervised in a sense that you do not have labels for your test set. But there is another level of unsupervised, of being unsupervised, that is not covered here. That's the case when we don't have access to Q of X at all, right? This is also an option. But this is harder, and again, just like I mentioned before, we must have at least something. We need to know at least something about Q of X. So one scenario that is discussed in the literature is that assume there are multiple domains. So it's not only 1 and 2 domains, just like in this unsupervised domain adaptation where one was training and the other one was test. But imagine you have like 10 different domains, and 7 of these domains appear in the training set. And the test set contains images from 3 more domains. Okay, and we want to use this information about the 7 domains that we have in the training set to generalize to the unseen domains. This setup is called domain generalization, and this assumes that we do not have access to anything from the test set. We also do not have access to images from the test set, which is the other 3 domains, for example, right? And the idea is that if you learn to ignore these several domains in your training set, if you can be domain agnostic in your training set, you should be able to generalize to the test set, which is also hard to describe in theory, but in practice you can consider that the domains are not very different, very far from each other. And basically this is the setup that we are mostly interested in, and we have tried to formalize it even more. So let's look at the setup that we are proposing. So consider setup where the change in the data distribution can be fully explained by some random variable C, which is correlated with both X and Y. Okay, so this is the setup. So imagine we have Y, and Y causes both X and C, but the important part is that X depends not only on Y, but it also depends on C. And C is the variable that is changed between training and test sets. So if we write it down here, so we have a joint distribution of X and C and Y, and this is decomposed the following way. We sample from Y, and then given Y, we sample C, and then given C and Y, we sample X. And same for the test distribution, and we know that P of Y and Q of Y are the same, so there's no label shift. We know that the distribution of C given Y is different. Okay, so this second term is different. And this term is also the same. So whenever you have fixed Y and fixed C, the distribution of X does not change in test and train distribution. So this is the only cause of the dataset shift here. We call this setup class-dependent domain shift because this is sort of a domain shift similar to this C acts similarly to the F in the previous slide. But on the other hand, the C itself depends on Y. So this is a little bit more complicated than the previous setup. This is domain shift where the shift can happen dependent on the class itself. So imagine that this setup allows the scenario where the camera itself depends on the label. Okay, so if you're filming some type of objects, you use one camera, and for other types of objects you use another camera, and this is changed from training to test. So this is a little bit more challenging setup. So again, here we assume no access to Q of X. So we should not be able to see the test data, but we also assume that P of C, this distribution of C objects, is quite rich in the training set. So if the goal is to learn a model that can ignore the effect of C in the training set, and we hope that it should work on the test set as well. One example could be classification of rare heart disease. So imagine that there is a heart disease which has some fixed prevalence in some population, so it does not change over time. So when someone is born, we know that there is like 1% chance that there is this heart disease. So whenever we sample a group of patients, some of them have this disease, and then we perform electrocardiography and extract heartbeats from this electrocardiography data. In this case, so X would be the heartbeats, C would be the patient, and Y would be the existence of the disease. So this satisfies this formulation because the distribution of sick people will be the same. The distribution of the prevalence of disease is the same, but then this is different because in the training set you have some patients, in the test set you have other patients, but then if you have a patient and if you have whether he's sick or not, the ECG, the distribution of heart patterns are fully determined by these two, and this does not change between training and test sets. And more synthetic example here. So imagine we have digits. We ask some people to write digits, but we ask them to write these digits in some colors. So imagine in the training set, which is the top row here, we color 5 digits only with these colors. We color 6 digits with these colors, and we color 9 digits with these colors. So we ask the person to write some digit, we give the color, and the person writes the digit. Okay, and in the development set or test set, we have different colors for these classes. So again, there is some correlation between colors and digits, but this correlation is changed from train set to the test set. And we want to be robust. So we know that there are 2 colors that were used for 5 in the training set. And if we teach our model to ignore the color itself, it should work on the test set also, right? Otherwise, it could simply look at the colors. If it's green, it's 5. If it's this color, it's 5. and so on. So this is the comparison of the three types of dataset shift I mentioned. And this is the method that we propose to solve the type of dataset shift, which was on the right, this one. The method is the following. So suppose we want to learn a representation Z of X, and Z should be rich enough to predict Y. It should contain a lot of information about Y, but it should have no information about C, so that we kind of want to ignore information on C, except for the information that is shared between C and Y, because C and Y can have some mutual information, they can be correlated, and if we want to predict Y perfectly, we need to have this information, but the other part of information on C should not be in Z. And this can be formulated as an optimization problem. We want to learn representation Z which has a lot of mutual information with Y, and mutual information was defined in Hrant's slides. I don't repeat that. And we also want to make sure that the conditional mutual information, so if we have information about Y, there should be no more mutual information between Z and C. Okay, and to solve this optimization problem, we can put this into our training objective with some coefficient beta, and then there is a lot of literature how to optimize this. We took this one. I don't want to get into details, but this is doable. This is not exactly this. This is an approximation only, but you can easily code this in PyTorch, so it works. So we tried this algorithm on this synthetic setup, so colored MNIST. We have only 3 digits, 5, 6, and 9. And basically you know the setup. So we want to learn on these colors, and we want to see if it generalizes to other colors. We have 3 types of development sets, or test sets, you could say. One of them is called quasi-development, which has the same colors as the training set. Then there is another one which has different colors from the training set. And then there is adversarial, which has the same colors as the training set, but with shifted labels. So 6 digits are colored with the color which was used for 9. Okay, and here are the results. So on the left, you have a regular model. That's what Hrant called ERM, which is empirical risk minimization, a regular neural network, convolutional. What it does, when it starts to learn, it gets to 60% accuracy and then jumps to 100% accuracy on the quasi-development set, which means that it learned to perfectly classify the digits, but this is only happens on the part of the development set which uses the same colors as the training set, which means that it probably memorizes the colors. It does not look at the digit itself, it just looks at the color. And to prove that, we see that the performance on the adversarial development set, which had the same colors but different digits, gets to 0 because it only looks at the color, and if you predict the digit based on the color, you would do mistake on the adversarial. So you would take this 6 and you would say that it's 9 because it has the same colors as the 9 had in the training set. And here is our algorithm, and you can see that in the beginning it starts very well. So all 3 development datasets have some sort of 90% accuracy. But then at some point, if you train more, it starts to overfit on the color. So it tries to get to 100% accuracy, which is the ideal. And it manages to do that on the green, on the quasi-development set. And whenever it reaches 100% accuracy here, the accuracy on the adversarial development drops to random. It's interesting to see that it doesn't drop to 0, but this is 33%, which is random. So we have seen that the algorithm that we proposed can solve this artificial synthetic problem, but with some caveat. It is hard to do model selection. Like, we draw these plots it means that we have access to the test sets, right? To the adversarial development set. What if we didn't have it? What if the only thing we had was the green line? How did we know that this point is better than this point? So right now we don't have an answer to this question. So if we do a very fair model selection according to the green line, the performance on the adversarial one would be 34%, which is terrible. But if we somehow had access to some of the data points from the test set, we could do much better. We could pick this one. But this shows that model selection is a serious problem. And this problem was very well highlighted in a very recent paper from Facebook. The paper is called In Search of Lost Domain Generalization. It performs experiments of several methods that claim to be domain generalization algorithm on 7 multi-domain datasets. They tell explicitly that domain generalization algorithm should be responsible for specifying a model selection method, and researchers should disclaim any oracle selection results as such and specify policies to limit access to the test domain. So in our case, we here explicitly say that we have access to development set so that we can pick the best performing model. Otherwise, we wouldn't be able to recognize that this model is better than this one. So basically, this problem is very common, and it is common for all algorithms. So what they did, they took 7 data sets for domain generalization. One of them is easy, it's this one. It is rotated MNIST, so you train on regular images of an MNIST and you try to run it on different rotations. But the others are much harder. So you can see here like an art, clip art, product, and a photograph. So imagine you train on the first 3 and you want to generalize on the 4th, or you train on the first and the second and you want to generalize to other 2. So what they did, they showed that on all of these data sets, if you do fair model selection, none of the algorithms that were proposed in the literature outperforms ERM. ERM is the simple baseline. So this is very intriguing. So if you do fair model selection, none of them actually beats the simple baseline. And our algorithm is not an exception. We tried our algorithm also on these data sets, and again, it didn't beat any of them. And the reason is that actually these data sets, these generalization data sets are very complicated. So it's really hard to take only 3 domains and to generalize to an unseen domain here. They did one more experiment with Oracle. So imagine you have access to some test data and you can pick your model accordingly. Again, none of the algorithm outperforms ERM, with one exception. There is one algorithm called invariant risk minimization. It significantly outperforms other algorithms on this colored MNIST dataset, which is different from our colored MNIST. But it's funny that this dataset was introduced in the same paper as IRM, so it's kind of tuned to this dataset. And in fact, 70% accuracy is not bad because they have a lot of label noise in their data. This is somehow connecting to Hrant's talk also. So if you, the ideal performance here would be 75, and they reached 70, which is fine. But again, it requires some careful early stopping with access to test domain. Otherwise, it doesn't work, as we have seen here. If we select the model based on the validation set, we end up with 52%, which is bad. Okay, so to summarize, here are the unsolved problems for our algorithm and the setups that we are looking for. There is no reliable way of performing model selection, and we still cannot find good results on real-world data sets. It's funny that there is this domain bed, but there are very hard to find relevant datasets with many domains. So my intuition is that most of these models can work if the number of domains is large, like 10 or 20, but none of these datasets have this many. And we tried finally, I show you negative examples, the datasets that we tried to solve but couldn't. One was spoken language classification with limited speakers. So you want to classify which language is spoken in this audio, but you have very limited speakers for each language, like 5 speakers for English, 5 speakers for Spanish, and you want your model to not overfit on speakers, but focus on the language itself. And we couldn't do that with our algorithm. There is some biological data set recently introduced at NIPS. Again, the variety in the training set is very limited there, so it's hard to beat the baseline. And again, on the domain bed, I already mentioned, these are simply too hard. Very few domains which are very far from each other. Like if you look at this domain net, for example, quick draw and painting, these are so far from each other that you cannot expect to generalize from one to another. That's it. Thank you for your attention. I passed the time a little bit, but I hope it's okay.
Thank you, Hrant, for the talk. If there are any questions to Hrant, you can post it in Q&A or chat in the Zoom, or you can move it to Slack. It seems like at the moment there are no questions, and I think since we are already more than 5 minutes into our 30-minute break, we can move to break now and come back at 11:30 Yerevan time on the next talk.
Yeah, there is a question which says, are your objective function is convex? No, it's not. I don't know with respect to which you're asking, but even without this beta, it's not convex. So this is the regular loss function that you have in your deep networks. We just add the term and it cannot make it convex anymore. Okay, I'm happy to answer questions on Slack. Thank you.
Okay, thanks again, Hrant. See you in like 20-25 minutes.